what is useful to know is for these lower quantiles, these models that use multi-generational family history did better for the lower risk. Okay? So using a model that allows, so using a model that's clinically, people say, oh, only use this if you have a family history and you're high risk. These lower quantiles did better from these models, and the same thing under 50. Okay? So how did they do in terms of discrimination? So area under the curve, again, tells you, ideally you want to be here. The only cancer models where you're here is like liver cancer or smoke, lung cancer, something where you have an incredibly high relative risk from one of the covariates. So, breast cancer, prostate cancer, whatever, they're all around 0.7. A coin flip is 0.5. These are not so great in terms of discrimination. But what's interesting, I guess, is, or I think maybe, is that the two models have almost identical discrimination, right? So even under 50, or the whole cohort, identical discrimination, but very different estimates of absolute risk. So this is our 10-year risk that's observed. Both models are still undercounting. But the Bodicea, without the non-genetic risk factors, this just has family history, is undercounting the most. Okay? So non-genetic risk factors matter. And we have to put some more non-genetic risk factors in the model that are not just age of menarche, number of pregnancies, these kind of things. So we need more environmental factors because we know environmental factors are related to breast cancer. So in terms of then a summary for this part, there's greater concordance between models when using a shorter time horizon. So that's why we stick to at least everything being within a 10-year risk. No model, cancer model, this is where the heart disease people have an advantage because all of their models were developed and you have a shorter induction time so you can have more out of forecast sampling and validation of your models. Cancer, it's incredibly difficult to find cohorts to validate. So there's not a lot of good out of forecast validation of these models. And both pedigree models had very similar discrimination. So just because your area under the curve is similar, it doesn't mean that they were equal because, again, you could argue the individual woman going into the clinic would care a lot more about the accuracy of the model and less about the discrimination. So again, the model with the non-genetic risk factors was closer to what we actually observed. And then finally, the model with the pedigree data performed better even in what you could argue is more average risk women than the Gale model did. And so the Gale model, in what's been published, had like a sensitivity of anywhere from 30% to 40%. And these, the Bodicea model and the IBIS model has a sensitivity that's more like 70%. So then, if we can then, I'll end with this last part about etiology then. So when I was a doctoral student with Mara Lee, her research and Long Island breast cancer, one of the major aims was looking at polycyclic aromatic hydrocarbons, which you can get from a whole host of exposures. This is a refinery. I remember my father used to always take us to the refineries in New Jersey and call these things cloud-making machines, which, is not so funny, but I guess it was more typical of the times when they would also smoke in the station wagons with the wheels, with the windows up. But in any event, so this is all the work from Long Island, where this was the largest case control study of its kind. What was really innovative about it is these are measurements from polycyclic aromatic hydrocarbon DNA adducts, which is a very difficult lab assay to do. And this study very much did support that polycyclic aromatic hydrocarbons were associated with breast cancer risk. And then, if you look at subgroups, particularly ones that have DNA repair, defined by DNA repair SNPs, you saw an elevation in that. And so we recently looked at, and this was just published last month. Now this is a teeny tiny study that we're trying to replicate with the whole breast cancer family registry. This is just the New York site. So it's really only about all prospective. It's a nested case control study. but it's really only about 90 cases, and then it was a 1-to-2 nested case control match. So what is it showing? So the Bodicea this is a 10-year risk. So again, the people within this area are very average risk. The people over here, these are the people who have really the BRCA1, the BRCA2, PALB2, DNA repair mutations. These are people that have higher risk, maybe a number of different variants. And so what you see is when you look at high exposure, so this is 90th percentile in terms of PAH exposure. So this was done in the same laboratory, Regina Centella. So this is looking at PAH addicts. When you look at the very highly exposed and high underlying susceptibility, you see very, very high risk. When you look, and this is all relative to the non-detectable, when you look at 75th percentile, you also see an increase. But you clearly have to have lots of exposure, and you have to be at really high risk. And the blue line is just the mean, okay? But when you look at this little quadrant here, these are all women who then would fall under that cut point. So these are more what you would call average risk women. And so this again is like supporting, what you see in like very large and robust studies like the Long Island breast cancer study, would be more like average risk like this. But again, supporting that the signal, when you see the signal, it's really high exposure and then high susceptibility. We looked at the same thing with smoking, so this is the same cohort, but now this is the whole prophecy. So this is now, closer to the 16,000, and so you can see that this is current smokers versus non-smokers. When you look in this little quadrant, again, this would be more the average risk. You're seeing, I think this is off a bit, but pretty low estimates, and then when you go up to higher susceptibility, it goes up. So finally, then I would just mention that for the risk factors where we didn't see any clear indication of an interaction, so that was body mass index, like I mentioned before, but also alcohol, we didn't have a clear interaction with that. So it still may be important when we think about the absolute risk reduction. So, this is a woman without any breast cancer family at one extreme, and family 5 year, this is one with much higher lifetime risk. So again, a point on a relative scale, because this is something that, individuals being counseled within these high-risk families, it's useful to know what your risk reduction could be. And so again, if we're thinking about more targeted prevention, the higher your absolute risk, obviously, the greater the reduction from even the same relative risk, the modest relative risk. So again, in terms of thinking about the summary, the tail may reveal exposures that can be targeted at a population level. pH, smoking, recency of pregnancy, all varied by this underlying risk, but body size and alcohol did not. But it's still important for these absolute risk differences. So if the tail can wag the dog, what about the puppies? So one of the major things that have been changing a lot in breast cancer, so this is the global map now, which was published by Torrey and colleagues, is that breast cancer is really increasing all around the world. So the high, areas for postmenopausal breast cancer still contain Australia, North America, Western Europe, but all of these other countries are increasing, and then globally about a third of all breast cancers diagnosed under 50. So even in individuals without a family history, the reality is they're being diagnosed at a time, and now their daughters have a breast family history. So we've been focused then on kind of blending the early life work and then the high-risk cohort work into a high-risk pubertal cohort, and really to focus mostly on what's going on with changes to the breast during puberty. And so we know that the breast changes in form and function during the fetal life, during the pubertal life, puberty, and menopause. So we've been focusing now on the next generation of girls from the Breast Cancer Family Registry, and then we have a separate, what we call like an average risk cohort that we follow alongside. And so some of this was building from our birth cohort work, but again, the birth cohort work that we did was all average risk cohort. and we had limited kind of repeat biospecimens. And there really wasn't, prior to when we started this cohort, there wasn't really any cohort that had these serial breast measurements. So the reason to look more at puberty is because even though age at menarche has been for many decades now a very well-established risk factor, it's been fairly stable in terms of the age of onset. It's about 12 and a half, but the age at breast development has been really changing. And so this work is from a prospective cohort in England showing that independent of age of menarche, that this age of breast onset had importance association with breast cancer risk. And then the time between the two, so even if age of menarche has generally been stable, the fact that breast development is changing quite dramatically all around the world, even in places where there's not an obesity epidemic. Some of the earliest age of breast development is in Hong Kong, for example, where they don't have an obesity epidemic. This time between those two events is also, in their study, an independent predictor of breast cancer. So we've been doing these measurements, so this is an adult, but this is what we do for the girls, and it's this optical imaging optical spectroscopy. So basically it collects measures. We do this directly on her skin. Every 6 months we bring her into the clinic, and we're also collecting questionnaires and that sort of thing. And then we have a group of collaborators at Penn that do behavioral research. And so this was work that they published to motivate some of the continued follow-up of these girls. And this is kind of the sobering reality to bring us back to those two kinds of worlds that people lived in, which is if you have a family history, it's your genes, don't worry about doing anything. And if you don't, then don't worry about your genes, which is completely false. Your genes matter for everyone, but so does your environment. And so here, this is what they published based on their following adolescent girls, which is girls with a breast cancer family history were starting to smoke. So they're clearly not getting the message that smoking is, one of the things that can affect them, as well as people without a breast cancer family history. So we have a long way to go to be able to make sure people understand that there's no kind of false dichotomy between those two. So here's just results that we just finished with our legacy cohort. And so these are now all girls that are not overweight. So when we looked at the girls that are not overweight as defined by the CDC 85th percentile, the girls in red here were those with any breast cancer family history, and they were starting to develop their breast sooner than girls without. When we looked at girls who were overweight, we didn't see that interaction. So it definitely was an interaction that was only detectable in girls who were not overweight. So finally, I have all these interim summaries, but I promise you this is the final summary. The most causal factors for cancer are found through observational design, so we shouldn't be ashamed that we do observational research. And family-based cohorts in particular are an efficient design to investigate really how the environment can be influenced by underlying genetic susceptibility and vice versa. And I would argue that just like with genes, finding these environmental signals within these family-based studies, these results are still very generalizable to the larger group. So again, what we hope then is Graham Colditch showed the impact you can have, if you start prevention here in midlife, which everyone knows you can change anything in midlife sometimes. But then, his group showed then the huge impact. So we can reduce breast cancer if we start them, but if we start earlier, you can reduce it even further, and these are estimates from Graham's group. But then, of course, a lot of these trajectories are started even earlier than that. So just like to, in closing, thank you again for the invitation, and to thank my colleagues at Columbia and throughout the Breast Cancer Family Registry. And if you don't know your family history, maybe to encourage you, because it's still very important. So, thank you.
Time for a few questions.
Andy, this one behind you. question. I learned a lot. One of the growth phenomena that you mentioned, I'm actually not familiar with, and I was wondering if you could explain what the adiposity rebound is.
Oh, okay. So kids go through different stages. You probably know with your own kids, of course. But one very rapid period of growth is the first year of life. So most boys and girls triple their weight during the first year of life. Some think that there's like this mini puberty going on. Some kids you can see breasts develop during that, like around 8 or 9 months, and then they regress. So the other important part of growth is what's referred to as this adiposity rebound, which is usually estimated, again, it differs a little for boys and girls, but around 5, 6, 7. So that's also a period where you see a lot of dramatic change in rates of adiposity. Height growth is a little different, as you know, because for girls, some of that, taller girls tend to have puberty earlier, but then their height growth stops. And whereas if the menarche is delayed, then they continue to grow. Yeah, so.
For any of the modeling that you've done within the family cohorts, have you guys done much looking at subtype-specific risk factors and whether some of these modifications, like looking at basal, I did see that you had done some, but I didn't know how much effort was going into that area.
Yeah, so for the prospective cases, we will have we're collecting all of that. For the retrospective cases, so most of those are all diagnosed from the 90s. So we have tried to get stuff, but it's definitely ER2 new is really not readily available on our retrospective cases. So that's what makes the affected baseline cohort a little challenging. But our prospective cases, we do have really good markers because most of them were all diagnosed in the last 10 years.
Yeah. It's just interesting to think about how the ability to do predictive modeling might be better for some cancer types than others.
Right.
So it's very interesting. Thank you.
So I want to actually follow up on Melissa's question. So I think you talked about the Gale model being like a coin flip, and at some point you said that, and the other models be just somewhat better than a coin flip. And so is that,
I think you said the coin flip would give you 50-50, but those were only slightly better.
Yeah, no, I'm sorry, I didn't mean to say that if that came out. With Gale, I think most models of Gale, it's around 0.68. All of them are not that different from each other in terms of discrimination, 0.6, 0.7.
But they're not all, but they're missing something. All those models still need refinement. I think that's what Melissa was talking about. What else, what is missing from the models to get at a much over 0.68 or 0.7? Are there other risk factors, or I think you alluded to what the other factors that should be added to the model to get better prediction?
Yeah, so they don't have any true environmental risk factors, right? So they don't have, so those are not in the model. The other thing that's really missing from a lot of these models is true interactions. So we think interactions will help explain and help discriminate. Like there's no interactions with family history in any of these factors. The other argument could be that for some of these cancers that a lot of it is just going to be, the de novo kind of, sporadic mutations, right? So that's the hard thing to get at. Yeah.
No predicting those.
Yeah.
Right.
Do any of those models include like breast density?
So the Breast Cancer Surveillance Consortia has their model that they use. We didn't look at that because in order to look at that, you already have to have a mammogram, which means for most people you have to be above 40.
Right.
So we're really focused much more on the younger women.
Last question?
Hey, Dr. Terry, thank you for nice talk. I also have a question about the risk assessment model. So how it can be applicable to predict survival, or what we can get some value from this risk assessment model to create a prognostic model?
Yeah, so a colleague of mine at a meeting the other day said, I have nothing to add but something to say. So I have something to say, which is, and it's all sort of what I think still has to be done for modeling of survivorship and modeling mortality after diagnosis, is all of the models that are used clinically are all based on molecular subtype. None of the models incorporate family history, which I just showed you, like still predicts second cancers, right? So, and the models themselves do not use risk factor stuff, even though all of your work too suggests that, your body size has a big impact on mortality just as much as a P53 mutation, right? So I think if there's any major area of research you want to work on, going forward, I think a big area is going to get better, survivorship models, right? So that incorporate non-genetic risk factors that we know are important, as well as family history.
CBCS will have all of that. Issues we're having CBCS, Mary Clark King is doing the Broca panel on CBCS 1 and 2 now, so we'll have a diverse array of data to predict something. So. Okay, well let's thank Dr. Terry.